Hey everybody, welcome back to Environmental Organic Chemistry with Lisa. So we're going to continue our conversation about hydrolysis reactions by looking at table 12.7 and from your textbook. This is a long table and there's just so much to talk about here, so I want to spend a little time on this. So this is a table saying, okay, look, if this is your backbone and then X is your leaving group, and X could be fluoride or chloride or bromide or iodide, then how fast are these reactions? And we know that fluoride, as leaving groups go, fluoride is the worst leaving group among these four. Chloride is better, bromide and iodide are about the same. So if you have a primary halide, right, where the halogen is at the end of the carbon chain, and iodide is your leaving group, the rate of hydrolysis, the half-life is 50 to 110 days, so a few months. If bromide is the leaving group, then you're looking at about a month. If chloride is your leaving group, you're looking at about a year, so about an order of magnitude slower than if bromide is your leaving group. And if fluoride is your leaving group, you can see how it says about 30 years, because the truth is, who's going to wait around in the lab for 30 years to see how fast fluoride reacts? So when you have a half-life of 30 years, basically that's, infinite. As far as we're concerned, that's too long to matter. So these primary fluorides are just not very amenable to falling apart, to being hydrolyzed. Okay, so now if we have a secondary halide here, for chlorine, it's now much faster. It's almost an order of magnitude faster. Instead of 340 days, it's now only 38 days. Because, why? Well, probably because you're forming a carbocation. If you were going by an SN2 mechanism, you would expect things to slow down because the secondary carbon here is more sterically hindered than the primary carbon was up here. So you would think that this would go slower if it was an SN2 reaction. So it must be an SN1 reaction going on here. SN1. And then for bromide, very quick, 2 days. Iodide, about the same, 3 days. Then if you have the tertiary carbon here, where it has bonds to 3 other carbons, and here's the leaving group, the bromide and iodide are so fast that you can't even measure them. Chloride is gone in 23 seconds. And fluoride will go, but it's still going to take you 50 days. So fluoride, just really not a very good leaving group. Here's our allylic system, right? If you lose the leaving group here, you could form a carbocation right here, and it would be an allylic carbocation. So this is a very favorable system to go by SN1. And so if chloride is the leaving group, you've got a half-life of a couple of months. If bromide's the leaving group, only half a day. Iodide is a leaving group, 2 days, so pretty fast. And then here's the benzylic system I was talking about. This would be a benzylic halide. If this leaving group leaves, then you get a benzylic carbocation. For chloride, if chloride's the leaving group, you're looking at only 15 hours of a half-life, so this is quite a fast reaction. Bromide, 0.4 hours. Iodide, probably too fast to measure, too difficult to measure, and definitely going to go by SN1. So the only thing here that very clearly goes by SN2 is the primary halides. Secondary and beyond mostly is going to go by SN1 reactions. This is another explanation in your textbook of some strange things that can happen. So if you release chemicals of this type out into the wild, you start to find some bizarre products. So you find the product where the primary bromide's gone, it bonds to a primary sulfur here, and you get the straight chain, but you don't get this branched thing, which is kind of, you don't get this branched thing, which is kind of strange. You do get this one and this one, but this here is not found. Okay, it's kind of odd. So the idea is that the first step in the reaction, some of this is going to go by hydrolysis to form the alcohol, and this thing is not a good nucleophile. So this is essentially a dead-end product. But if you react with sulfide, you can form this thing, which can lose this proton to become negatively charged, and then this thing is itself a good nucleophile. So it becomes a decent nucleophile and then goes in and attacks another molecule of your reactant, stuff that was added to the system, and that's where you get these products from. So kind of an interesting reaction schematic depending on SN1 and SN2 reactions. This is a really large table, table 3.7. 13.7, excuse me. And it's showing you sort of the range of reaction rates that you can expect from highly halogenated alkanes, right? Alkanes means single bonds. And you guys know that TCE and PCE have double bonds, and they are not alkanes, they are alkenes. And they are not shown in this table anywhere because TCE and PCE and all of their daughter products that have double bonds are not going to react by SN1 or SN2 reactions, period. They will not. If they did, a lot of environmental scientists would be out of a job because groundwater contamination with TCE and PCE is a big, big problem, and it wouldn't be a big problem if they could just react with water. So here's dichloromethane. That could go by an SN2 type mechanism. And you notice, though, that the half-life of this reaction is 700 years at a pH of 7. So this is not a great rate of reaction, and it's because the chlorine is big enough that it's sterically hindering any kind of SN2 reaction. Not going to go by SN1 because you'd have a methyl carbocation, which is not very stable. So this actually hydrolyzes very slowly. Here's trichloromethane, same deal, 2,000 years for a half-life, so this does not react quickly at all. One of the interesting things here is to look at the activation energy, 123 kilojoules per mole. That's really, really high. So this is the neutral rate constant, which means it's the reaction with water. And because water is considered to have a constant concentration, this is expressed as a pseudo first order rate constant. Over here is the reaction with base, meaning hydroxide. It's a second order rate. So it is expressed in units of per molar per second. And so you can't directly compare this number with this number, right? Because what you'd have to do is multiply this number by the concentration of hydroxide. So at a pH of 7, concentration of hydroxide would be 10 to the minus 7th. So you'd multiply this times 10 to the minus 7, and you get about 10 to the minus 12. So they would actually be kind of roughly equal. And it turns out the pH, that's what this is. This is the pH at which the neutral and the base mechanism occur at the same rate, so it's about 6.5. So in other words, this is reacting both with water as the nucleophile and with hydroxide as the nucleophile. And at a pH of 6.5, those two reactions are equally fast. Here's tetrachloromethane, really not reacting at all. I don't know why they even give you a rate constant here. But, 40 years, it's really not going anywhere because it's just way too sterically hindered to be attacked by a nucleophile. Tribromomethane, kind of a similar deal, 700 years, it's not going anywhere. Here's 1,2-dichloroethane, so a chlorine on each carbon. Does react, but the rate is very slow, 70 years. 1,2-dibromoethane, so the difference between these two chemicals is the leaving group, right? The leaving group is chloride here, the leaving group is bromide here. And so instead of taking 70 years to react like 1,2-dichloroethane, it's now only 6.5 years for the dibromoethane. So that's just an example of how much better a leaving group bromide is than chloride. 1,1,1-trichloroethane, much faster, about a year. Well, that's strange. How does that work? What's going on there? One of the things is, look at the products. How on earth are you forming this double bonded product? Well, we're going to talk about that in just a minute. Here's 1,1-dichloro-1-fluoroethane. So the difference between this and this is the difference of a chloride and a fluoride. Much slower chemical reaction going on here. Similar activation energy. Notice that these activation energies are all pretty big, 100 kilojoules per mole or more. And then here's 1,1,2-trichloroethane, and you notice that the main product is 1,1-dichloroethene, or sometimes called 1,1-dichloroethylene. So where did we get that double bond from? That's very strange. Now, this is not a fast reaction, 140 years, but it does happen. So then there's some more examples here. 1,1,2-tribromoethane, very similar chemical, except now bromines instead of chlorines. And it reacts pretty quickly on the time scale of only about a year. 1,1,1,2-tetrachloroethane, 45 years, quite slow. But if you just rearrange it a little bit into 1,1,2,2-tetrachloroethane, all of a sudden you go from 45 years to 160 days. Like, what is up with that? Why is that so fast? And how are we forming this double bonded compound? And also, are we happy that we converted 1,1,2,2 tetrachloroethane to trichloroethylene? That's not a good thing. Here, we're converting pentachloroethane to perchloroethylene, or PCE, on a time scale of only 3 days. This is not a good thing. PCE and TCE are big groundwater contaminants that we worry about a lot. So what's going on here? And also, by the way, notice DDT being converted to DDE. This is a hydrolysis mechanism. Time scale of about 7 years. So this is why most of the DDT that's been released to the environment has converted to DDE, because, DDT has been banned since the 1960s. So it's had plenty of time to undergo this reaction. So what is going on here? Why are we forming these double bonded compounds, and why are some of these reactions happening much more quickly than we would expect from the SN1 and SN2 reactions? Well, the answer is that they're undergoing an elimination reaction. And so sometimes this is called beta elimination. Should be a beta there, beta elimination. And this can also be called dehydrohalogenation. D meaning you lose something, hydro meaning you lose a hydrogen, and halogen meaning you lose a halogen. So here's the hydrogen, here's the halogen. So we have a hydrogen here, we have a leaving group. This could be a chloride or a bromide. They both get gone. These electrons don't go with the hydrogen, because the hydrogen's gone as a proton. So these electrons have to go somewhere. These electrons swing in here to create this double bond, and then the L leaves as a leaving group. And so where does the nucleophile come in? Well, the nucleophile attacks here at the proton, because this is a nucleus, right? Protons are positively charged. Nucleophiles are looking for those positive charges, and they go in and attack here. Okay, so this is important for molecules in which you have multiple halogens, and because they're big, they block the SN2 reaction, but they're also electron withdrawing, and so they're pulling electron density away from this proton, and they're rendering this proton partially acidic, having a large delta positive, a partial positive charge. And so you have to have the right geometry. You have to have the proton here right next to the leaving group. And when you get that, you can have a reaction that is bimolecular, because it involves the nucleophile, which might be hydroxide, and also this backbone, the halogen, the compound that's reacting. So the rate law, the rate is equal to minus K. This is a second order rate constant, so it has units of per molar per second, times the concentration of the nucleophile, let's say it's hydroxide, times the concentration of the backbone. So this is an elimination mechanism, and it's bimolecular, meaning that its rate law has two species involved in it, and so that's a second order rate constant, and so we call it E2, the E2 mechanism, and this can be important in a lot of environmental systems. So the transition state of the E2 mechanism, again, the hydroxide or whatever the nucleophile is, will come in and attack not at the carbon, because those are sterically blocked by these big chlorines, but it will come in and attack at the proton. Okay, and then it pulls off the proton, and one of the chlorides leaves, and you get the double bond left behind. So in any system where we have a chemical that could be reacting, if it has a decent leaving group, it could be reacting by a lot of different mechanisms. You could have the pseudo first order reactions here with water. You could have second order reactions here with hydroxide as the nucleophile, and you could have potentially other second order reactions with other nucleophiles. Okay, so the rate law would depend on all of these things: the pH, the rate constants of the neutral and the base catalyzed reactions, for straight up substitution, or for elimination. That's what the EN is, nucleophilic elimination, elimination base catalyzed. And so the observed rate constant could be a very complicated function of all of these things, which is why it's kind of difficult sometimes to just write a rate law. And so sometimes we just refer to things as a half-life. We just say, oh, half of it disappeared. I don't know why, I don't know where, I don't know how, I don't know when, but half of it's gone, and I'm going to call it a half-life. So not only can the rate depend strongly on pH and also on temperature, but the products can depend strongly on pH, temperature, and what other nucleophiles are around. So again, if you have these reduced sulfur species around, they could be be acting as nucleophiles attacking your chemical and forming some strange sulfur-containing products. But remember, again, this is all still for chemicals that are aliphatic alkanes, meaning they are sp3 hybridized. They have 4 different things bonded to carbon. Vinyl compounds like TCE and PCE, and also aromatic halides like chlorobenzene or like PCBs, they're going to be unreactive to all of these types of mechanisms. It just doesn't happen for them. This is only for things that have single bonds, sp3 hybridized aliphatic compounds.